We have exam 3 next class period. And the topics are going to be everything up through linkages. And so there's not going to be any rotating coordinate systems. So I would be happy to answer questions. Otherwise, there's an example problem that we're halfway through that we're going to do another way, and I have another example to do after that, but those are rotating coordinate system things. So are there any like homework problems or anything that you have questions about that are related to the test?
I have one. I'm not sure if this covers the test, but Friday the 25th.
Yeah.
I looked at your solutions, and I got something else.
Okay. This is the cylindrical coordinates one. What?
That's the rotating coordinates.
Yeah, it is rotating. Yeah, it's not going to be on the test.
Could you just go through B then?
Sure.
Just the acceleration.
Yes.
Looks like you did
So
fine.
this is from Friday the 25th. And we could, does anyone just have that equation at their fingertips, the expression for the acceleration in polar coordinates? Otherwise, I'd have to rederive it.
I have the whole thing.
Okay.
So
Okay.
The equation is R double prime,
Okay.
or R dot double dot,
Yep.
minus R theta dot squared.
Okay.
And then R theta double dot plus 2 R dot theta dot.
Plus 2 r dot theta dot. Okay. And then is this cylindrical, or it looks like this is just polar, so that's all we need. Okay, and so for this, r as a function of time is sine of t. So r dot as a function of time is cosine of t. So r double dot is negative sine of t. Theta is cosine of 5t. So what does this motion look like? Can you picture what's going on here? Okay. Oh, I like your honesty. Well, it would be circular motion if theta was like an increasing function, but this is going to be sort of like oscillating up and down because that, theta determines if my arm is pointing at the particle, the radius is doing whatever, right? But my arm's pointing at the particle, and my arm's doing this sinusoidal function, So this particle is doing something like this. It's not continuing around in a circle. Okay, so theta dot is negative 5 sine t. And theta double dot is negative 25 cosine t. And then, yeah, all you do is, yes, thanks. So yeah, all you're going to do now is, plug these functions into, so the acceleration function.
Does anything funny happen with that theta dot squared?
No. So, we just have negative sine of t minus sine of t times, let's see, okay, minus sine of t times theta dot, so that's negative 5 sine of 5t squared. And then the theta component is sine of t times negative 25 times cosine of 5t plus 2 times cosine of t times negative 5 sine of 5t.
I think in your answer to cosine of
Okay.
I'll think about that.
I did those solutions a couple years ago, and I was stupider then.
And then when you set the, I think the next question is theta, when is the coordinate system equal? You just set theta equal to 0.
Yeah, so the idea there is the polar coordinate system is doing this. Well, the origin is staying in the same place. It's doing this. The sort of implied inertial coordinate system is just sitting here like this. And so those line up whenever theta is equal to 0. So if you just find the time when theta is equal to 0, you can measure the acceleration in the inertial one, measure it in this, and then they need to match. You could do it at any instant once you find that theta by using a rotation matrix. And then they need to match at every instant once you use a rotation matrix to re-express them, in a new orientation. Any other questions about that one? Okay, that one's not related to the test, but it's related to a test. Any other assignment questions?
Can you give us answers for the exam?
I would if I had written the exam already, but they probably wouldn't be the right answers. Okay, so ready to go on? So this was, I think, from Wednesday. I don't think we talked about this on Friday, but we were working on this problem where we had an arm like this and an arm like this. And these were each 1 meter long. And this one that I was calling body 2, this is body 1. Body 2 is rotating relative to body 1 with an angular velocity of, the angular velocity is actually 20 radians per second squared, and the angular acceleration is the velocity is 20 radians per second. The angular acceleration is 10 radians per second squared. Those are both in the same direction, so is that speeding up or slowing down? Yep. And this one is rotating relative to the wall at 10 radians per second and has an angular acceleration of 15 radians per second squared. So is that one speeding up or slowing down? Slowing down. And we're trying to calculate the acceleration of this point P. And we did it once. We did it once with a coordinate system rotating with that arm, body 1, with the origin fixed here at A. And now we're going to do the same thing with that coordinate system still, it's changing orientation along with body 1. So as body 1 rotates the way we did it before, this was doing, well, it was staying in exactly the same spot but just changing orientations. Now it's going to change orientation and move as body 1 goes up and down. Okay? And we have to get the same acceleration for P. So the first one we did was a coordinate system rotating with body 1 with the origin fixed at A. The second one, coordinate system rotating with body 1 with the origin at B. Okay, so the origin isn't fixed anymore. And so what are we going to have to do differently for this calculation? That's right. We'll have to use relative motion. And is there any reason why we should do this? I mean, it gives you a little flexibility. I mean, I think if you get to choose your coordinate system like you do in this case, you might as well always make the origin non-accelerating. You know, so I would choose the origin to be at A. But you need to know these kind of calculations because there are times when your data comes from a coordinate system that you don't have any control over, you know. And so that's when an approach like this would be relevant. Like, well, we can't mount a camera at A because of this or that reason, but we can mount a camera at B, and you need to be able to calculate the accelerations based on the data you get from that camera, you know. Okay, so the acceleration of P relative to the ground is equal to the acceleration of P relative to the origin plus the acceleration of the origin relative to the ground. Let's do this one first. So this one is circular motion of that point B. Okay, so the acceleration of the origin relative to the ground, we're going to use the watermelon equation, so that's alpha cross R plus omega cross quantity omega cross R. So what's alpha? If we're tracking the acceleration of this point is what we're trying to find. Right, and is it positive or negative, and what's the coordinate axis that it's about? So yeah, if we're using, right, so if we're lining this up with x that way and y that way, then alpha, alpha is going to be equal to 0, 0, positive 15. And what's the r vector? This kind of thing can get so tricky, like can be so confusing. But remember, if we're tracking the circular motion of this point, that r vector goes from the center of the circular motion to the point that we care about. Oh, so, right, so just like you said. So I got confused. It can be so confusing to me. So negative 1, 0, 0, right. And then what's the angular velocity? That's right, 0, 0, negative 10. Okay, so the acceleration of the origin relative to the ground is 0, 0, 15, crossed with negative 1, 0, 0, plus 0, 0, negative 10, cross quantity 0, 0, negative 10, crossed with negative 1, 0, 0. Okay, can someone plug that in? Okay, 100, negative 15, 0. And now we have to go on to the acceleration of p relative to the origin. And for that one, we're going to use the rotating coordinate system equation. So I'm going to write that as, that's the acceleration of p observed plus the angular acceleration of the coordinate system crossed with the position vector plus 2 times the angular velocity of the coordinate system crossed with the observed velocity of p and then plus the angular velocity of the coordinate system cross quantity angular velocity cross p. Okay, so if you're fixed, so if the observer is fixed at B and rotating with body A, what's the circular, that's the answer. What's the motion that you see for this point?
Circular.
Yeah, good. Yeah. So we just need to figure out the velocity and acceleration of this point coming from that circular motion around that axis. Okay. Since we're fixed with body 1, we don't notice any of this stuff. We're just seeing that point P move around like this. Okay, so what do we know about the observed velocity of P? Well, what's the equation for velocity with circular motion? Yeah, omega cross r. And so we have to think about what that omega is and what that r is. Okay, so what's omega? Yep, that's the 20 radians per second, and then what's the sign and the axis? The axis is x and the sign is negative. Yep, that's right. So negative 20, 0, 0. And what's the r vector? Right, 0, negative 1. And that is not a function. That's just, at this snapshot, that's what that r vector is. And so velocity of p that's observed is equal to negative 20, 0, 0, crossed with 0, negative 1, 0. And so you get 0, 0, positive 20. And how do we calculate the observed acceleration? What kind of thickly membraned fruit? Yes. Okay, we already have omega and r. What's alpha? That's right. That's in the same direction as the angular velocity. So that's negative 10, 0, 0. And so acceleration of p observed is negative 10, 0, 0, crossed with 0, negative 1, 0, plus the angular velocity, negative 20, 0, 0, crossed with the quantity, negative 20, 0, 0, cross 0, negative 1, 0. And what do you get for that? 0, negative 400. Okay. 0, positive 400, 0. 10. Okay, thank you. And what's the angular velocity of the coordinate system? Zero, right, 0, 0, negative 10. And what's the angular acceleration of the coordinate system? Yep, 0, 0, positive 15. So now we should be ready to roll. I guess what's the last thing we need is the position vector. So what's the position vector of P? Right. 0, negative 1, 0. And so the acceleration of P relative to the origin is equal to 0, 410 plus 0, 0, positive 15 crossed with 0, negative 1, 0 plus 2 times 0, 0, negative 10 crossed with the observed velocity vector, which is 0, 0, positive 20. Plus 0, 0, negative 10, cross quantity 0, 0, negative 10, cross position vector 0, negative 1, 0. Anybody have this programmed into your calculator? goes away. I got 15,510. Okay. Yes, thank you. And so then put this all together and you get that the acceleration of P is equal to 15,510 plus what we got for the acceleration of the origin, 100 negative 15, 0. And so we get 115, 485, 10 meters per second squared. And that matches what we got with the other coordinate system. Any questions about that? Yeah.
It's not necessarily a question. I know we would never do this, but for doing P relative to the origin, why wouldn't you just use the watermelon equation then? Why do you use this equation?
We use the watermelon equation to figure out. So we did use it because we were figuring out to figure out what the acceleration of P looks like in that coordinate system. We use the watermelon equation because to an observer in that coordinate system, P is just in circular motion. So we did use it. But then we had to make corrections because that coordinate system's axes are changing orientation. And so, yeah, so so what that coordinate system observes as the acceleration, which comes from the watermelon equation, isn't quite right because its axes are changing orientation, and that's why we need to like, you can think of this equation, this big, ugly, rotating, where do I have it? This equation, you can think of it as, yeah, we did use the watermelon equation to figure out what acceleration was observed in that coordinate system. But these other three terms, those are corrections that come from the fact that what we observed in that coordinate system isn't the actual thing because that coordinate system is rotating.
So it's relative to the ground and you just use the water.
That's right. Yep. So all of this stuff comes from the fact that I dot, J dot, and K dot are not equal to 0. So those bring in those extra adjustments, correction terms. Any other questions about that? Okay, let's do another one.
What if,
Mm-hmm.
let's say if, so this is going to be, I think it's going to be more complicated now.
Okay.
Let's say we have this problem,
Yeah.
and we're trying to figure out well, what we did right now. But what if we're trying to do it the same way, except the whole system is
Mhm.
rotating?
So yeah, like if you have this, but then what I have as a wall here is also on something that's rotating.
Yeah.
Okay, so you can just keep piggybacking. You can do it as many times as you need. So what we would have gone all the way through to find then would be the acceleration of p observed in this bigger rotating coordinate system. And then we would have used our rotating coordinate system correction, this thing. So everything that we calculated would now be the acceleration of p observed, and we'd include the correction coming from the, and so you could do that. So you start with the observed in one coordinate system, add the correction to go to the acceleration that's observed in the next coordinate system, then add that correction to, and you can do that as many times as needed. We're only going to do it in this one step, but, or are we? I've never really thought about that before, but that seems like a good problem set question.
Now everyone's going to hate me.
That's all right. Okay, let's do another one. So let's say you have this object fixed to the ground, and there's a little sleeve that can rotate around it. And that sleeve is connected so this disc rotates around an arm that's connected to that sleeve. Let's say that this distance is 1 meter. And this angle is 45 degrees. This disk is rotating with a constant angular velocity of 10 radians per second. And this sleeve is rotating about a vertical axis at 5 radians per second. Those are both constant angular velocities. And we want to know what's the acceleration of this point P, given that the disk radius is 0.6 meters.
Just like the gyroscope.
Yeah. And we could also do this one with the origin at 2 different locations. Let's just start with the easiest one, and then we'll see how long this takes. But I'm going to call this point A, this point B. This rotating sleeve will be member 1, and the disk will be member 2. Which of these two bodies is the horse? Yeah, right. So body 1 is the horse. So we know that the coordinate system is going to rotate with that arm.
Give an example where it's like a carousel and a horse.
Don't tell me what I should do.
Fair enough.
Where what?
Where the horse is the actual horse.
Oh,
And
yeah. Or if it's on the carousel, then the horse is the cowboy and the carousel is the...
You can like design a horse.
Yeah. I should always just draw the body. Yeah, right. So it actually looks like a horse.
Make people more confused.
Okay. And then, so we know what body the axes are rotating with. We have to decide where to put the origin. So if I'm not specifying where to put the origin, what's the easiest place? So I've given you two choices, A and B. Yeah. So if we put it at B, what's the complexity that comes up then? That's right, exactly. That point B is accelerating because it's moving in a circular path like this. And so we'd have to use relative motion if we put the origin there. So the easiest origin location is A. Because that's not accelerating. And so let me draw like a straight-on view of what we're looking at. So there's that, and that. And the coordinate system is here, x, y. Okay, so we're going to use the equation that says the acceleration of p is equal to the acceleration of p that's observed in that green coordinate system plus the angular acceleration of the coordinate system crossed with p plus 2 times the angular velocity of the velocity of p, this is p, that's observed in the green coordinate system, plus angular velocity cross quantity, angular velocity cross p. And so the trick to all this is just choosing the right values of these variables that go into it. So we have to choose position vector. We have to calculate the velocity and acceleration that are observed. And we have to give an expression for the angular velocity of the coordinate system, the angular acceleration of the coordinate system, and that's it. Okay, so take a few minutes, compare answers to each other, talk to each other, and figure out what these 5 values are. Okay, a couple of them you'll have to calculate. Okay, so what's P? Okay. Anybody have any trouble coming up with expressions for the position vector? Oh yeah, it seems like that's a little high, isn't it? Well, it should be 0.7071 plus 0.6 times .7071. 1.13? Okay. But this one's right? Okay. 2828? Do what? Yeah. So that's this vector is a length of 1 times cosine of 45 sine of 45. This vector is 0.6 times cosine of negative 45 sine of negative 45. We're trying to calculate this position vector. And so you can get that by just adding up those two vectors. And then what's capital Omega? Yeah, 0, negative 5, 0. So that's the angular velocity of the coordinate system.
I'm sorry, how did you do that?
So
Oh, just
there's the coordinate system. Yeah, the axis of rotation is this. When we're doing the circular motion equations to talk about the observed velocity and acceleration of p, we're going to have this funky axis of rotation. But on this one, the coordinate system is just spinning around in a vertical circle. And then what's capital Omega dot? 0. That's because it's constant angular velocity. Okay, so now the next thing we have to do is calculate the velocity and observed acceleration, the observed velocity and observed acceleration. And that is going to be a circular motion about this funny axis. What's the axis of rotation? Yep. And so that'll just be, so you can express that axis as cosine and sine of 45 degrees. And then multiply that by your magnitude of angular velocity. It is going, in this case, so it goes according to the right-hand rule. So it's going to be...
we don't have to rotate, right? Like, we don't have to multiply by rotation matrix.
Nope. You can just calculate the direction of that axis. The right-hand rule says that your angular velocity vector is going in this direction. So that's just in the direction of positive, cosine of 45, sine of 45. And then multiply that unit vector times 10 radians per second. And I guess we'll go through this on whatever day it is, Friday. Okay, so test on Wednesday.